Hello, everyone. Welcome to the recording of the panel event on the measurements of the Hubble constant using the distance ladder as part of the Cosmology from Home Conference 2021. I'm Marika Asgari, and I moderated this panel event with the help of Nico Shurchevich and Matthias Vanderbilt. All of the organizers contributed to the planning of this event. The main goal that we set for this event was to pursue understanding in a collaborative way. And as such, disagreements were very welcome as long as they followed this goal. If you're watching this during the conference, you can follow up and ask questions using the Slack channel, or you can find any of the panelists in Sokoko and meet with them informally. So I will shortly give you a little introduction to this topic, and then we can go on with the event itself. So one of the primary ways to measure the Hubble constant is using the distance ladder method. We can measure the Hubble constant if we know distances to cosmological objects, as well as their velocities, radial velocities, that is. To get the velocities, we can use redshift, but the distances are trickier. And this is where supernova type 1a come in handy, because they're very luminous, so we can see them in the Hubble flow. And also they are standardizable candles due to their period and luminosity relation. But this needs to be calibrated. And that's what the distance ladder method does. So a typical distance ladder consists of 3 rungs of the ladder. In the first step, we're looking at nearby objects for which we can measure geometric distances, such as parallax. In the second step, we look at intermediate objects, such as bright stars, with calibratable, standardizable luminosities. And in the last step, we're looking at further away objects, supernova type 1a, in the Hubble flow. Now, the main thing about the distance ladder is that we can calibrate each step using the previous one by finding objects for which we can measure 2 different distances. For example, let's say we chose Cepheids as our second rung. In this case, if we find Cepheids that are close enough to us, then we can measure the parallax distance to them and calibrate their luminosity. And the same goes for calibration of supernova using Cepheids. Now, in this panel, we mainly focused on the second rung of the distance ladder. And aside from Cepheids that I just mentioned, we can also use populations of red giant stars. Both Cepheids and red giants are luminous stars, so they're good candidates for going to further out distances, but they have differences as well. Cepheids, for example, are young stars, and they pulsate with a luminosity distance luminosity period relation, and this can be standardized. While red giants are old stars that populate a particular part of the luminosity and color diagram. And this is called the red giant branch. As these stars age, they heat up and they move up the red giant branch until they undergo a core helium flash, and then they lose their luminosity dramatically and fall out of the branch. And where this happens is called the tip of the red giant branch. And this has a known luminosity. So if we have a large enough population of red giants, we can measure the tip of the red giant branch, or TRGB. Both of these stars have their own challenges. Both of these methods have their own challenges. Cepheids, for example, being young stars, they tend to live in populated areas of lake-type galaxies, where blending of the sources and also dust extinction can be a problem. On the other hand, the tip of the red giant branch can only be measured for a population of red giants. So selection effects and the size of the population can be important here. And because of these challenges, when we use these two methods, we get different results. So for example, here you can see the measurements of H0 versus year of publication and how the distance ladder measurements using Cepheid and CMB estimates of H0 have drifted apart. And in fact, the difference between these points is what makes this topic very interesting. And then TRGB measurements came in later on, which sit right in between them. In this panel discussion, we didn't talk about CMB results and instead only focused on the distance ladder, and in particular, these 2 points. Okay, that's the introduction done. Let me introduce the panelists. We have Rachael Beaton representing the CCHP team who use TRGBs. And then we have Dan Scolnic representing the SHOES team who use Cepheid. And we have 2 independent panelists, Behnam Javanmardi and Suhail Dhawan, who've done their own independent analysis using Cepheid. So let's welcome all the panelists and start the panel discussion. We're going to start with the first question, and that's the most obvious question. And that is, do you think these Cepheid and TRGB results, the ones that I just showed at the end, from the SHOES and the CCHP team are consistent, and why? I'm going to start with Dan and then continue with the others.
Yeah, first, thanks for having me. I'm really excited to be part of this and happy that I navigated Sococo. Are they consistent? I feel like they are close-ish, but not as consistent as I would like them to be. So roughly there's like a 0.06 meg difference. There's different ways to account for it. You could say that's 2 sigma-ish or 1.5 sigma, depending on how you're doing it. In the last Freeman et al. Paper, I think it was kind of pushing towards more significance in the discrepancy between Cepheids and TRGB. So yeah, I would sleep better if they agreed more. And what's nice is that we can look at the same galaxies for Cepheids and TRGB. So you can kind of do these direct comparisons, but you still have to kind of choose where to anchor them, and then see if some differences in those anchors as well. So it's kind of hard to trace where differences come from. But overall, I kind of feel like the trend right now is towards not so great consistency. That being said, I am cool with kind of averaging between the two. So I pass that off to other people.
All right, thank you. So maybe Rachael can give an answer.
Yeah, I think I'm on the same fence as Dan. I would sleep a lot better if we agreed and, better within our uncertainties. But I do think it's, considering how different the 2 analyses are, I think it's really good that where we do agree, we agree really well. So in the nearest galaxies, we actually almost always agree within our respective uncertainties. It's only when we get to the most distant galaxies, which is actually like the most important realm of this distance measurement, because that's where the number of supernova hosts starts to increase, because we're effectively volume limited by our supernova calibrators and by our techniques. We start seeing the distances really bounce around, and it's hard to understand there because we're literally doing the hardest measurements. These are really, really hard. And we make a lot of different choices, and we try to account for all of our choices and our uncertainties, but we're still seeing some level of disagreement in these more distant galaxies. And I think we are not seeing it go away as we add more nuance to what we're doing, as other teams look at our data, as different teams publish results. It's not resolving itself as if there's some key missing piece that we haven't found. And I'll also say very clearly that when I stare at these numbers, which I have nothing jumps out at me when I read the different papers. Like nothing comes out at me as being like, oh, obviously this is where we made the mistake. Whatever the difference is, it's incredibly nuanced. And I think we're probably not going to find it without sitting down in panels like this and talking to each other.
All right, let's start with this panel and then see maybe what could be the solution. Right, so Behnam, do you want to maybe make a comment about this?
Well, first, Suhail, thanks for having me here. Honestly, no, I had more questions about this than having having a clear opinion on the question you posed. But part of it was answered by Rachael, that the difference starts when we go to the larger distances. But my first impression by looking at the figure 6 of Friedman et al. 2019 was that maybe there shouldn't be no systematic difference. So
let me stop you 1 second.
Sorry.
Pius, could you share the figure 6 of Friedman 2019?
And maybe I can just say the question that is I'm missing where exactly is the difference? Is which galaxies are causing the problem?
Well, yeah. So I mean, in some of the kind of calculations we've looked at, it's about 0.06 mag. So it's kind of hard to see on if you look at the bottom panel here. And I think what's also tricky, and a lot of papers have gone into this, is the specific uncertainty weighting of every galaxy for both the TRGB and the Cepheids can pull more or less. So there's different ways to kind of cook that up to be bigger or smaller. But just for kind of some scale, you know, the Planck tension between shoes and it would be with shoes is 0.2 mag on the bottom panel, and the difference between shoes and CCHP is 0.06 mag.
So in our slide deck, slide 17 in our slide deck kind of zooms in on that bottom figure, and then I labeled the galaxies, which might help. Yeah, sorry. I tried to message someone, but I got lost. 17, so 2 more, maybe one more. Yeah, that one. So this is basically that bottom panel, except now I've labeled the 10 galaxies in common and kind of zoomed in so that you can see. And there's that 0.6 mag in this weighting, as Dan said, this weighting of the uncertainties. Because really weighting by the uncertainties gives you different results. And then but the scatter is about 0.17. And this is just comparing the distances directly. And so for something like N4038, 4039, which is the antenna galaxy, like I could easily see how either one of us could be wrong on that one. Or there could be some systematic problem. But for some of these others, they're pretty textbook measurements for either team. And so it's really hard to see something inherent to the technique on either analysis that could be causing it. Like if it were all the ellipticals and all the spirals, you'd be like, okay, yeah, got it. But this is a little more complicated. I think that's the only one that I can explain, because even this one here, 4424, which only has a handful of Cepheids in it, we still, even though the uncertainty is very large, we're still like really close.
Suhail, do you want to say something? No?
So my question was actually on 4424. Is there a way in which the Cepheid distance can be improved for that? Because I really like Supernova 12 CG for no real reason, but it's a really cool supernova. And I was just like, if there's a way in which, because you know, it could move within that error bar, it's pretty big, but that would be like another way to improve upon the current data, while of course at the same time getting a bigger sample, maybe like 16 or 20 that actually have both TRGB and Cepheids? Is that a possibility?
Yeah, definitely. So kind of Shoes has its next big paper coming out, I don't know, hopefully sometime soon. And so we're doubling this calibrator sample, but also kind of people went back and rediscovered and found more Cepheids in a lot of these galaxies. So a lot of this will get better. From kind of what I've seen, I'd say this like 0.06 megs doesn't seem to be really going away. But the analysis isn't quite done. But yeah, that's definitely doable and happening right now.
Maybe a follow from this plot. I'm not sure whether from the plot it's necessarily so that it's the more distant ones that are worse off. But like my question was, is the fact that the Mesa galaxy Cepheid and TRGB distance, or like the Mesa and the Sartu Cepheid distance are off by a couple of sigma or more, is something that's probably causing more lack of sleep, or am I just having a bad sleep schedule? Like because that's something that like I didn't really notice how big that difference was, and where would that be coming from?
Sorry, which one are you pointing at, Suhail?
The Mesa galaxy. So is it not more like about a tenth of a mag difference? The reason it's just close by. So like in terms of feasibility, that shouldn't be like an issue, should it?
Sorry, which one is that?
Sorry, NGC 4258, the one with the water Mesa, not the supernova host, the primary anchor. So I was just saying,
it's not on this plot, is it?
No, it's not on this plot. No, sorry.
No.
I meant like, I wasn't sure whether from this plot I saw a distance trend, and I was just wondering whether there is like whether the distance or like actual feasibility of pushing the ladder forwards is the main sort of driver behind the discrepancy, or is there some stuff like closer with the primary anchors where differences can be understood better? So that was my question.
If you go to the next slide, it has a more, so this slide, this is also from Wendy's paper, but then I've annotated it a little bit more for talks. So this is looking at literature, Cepheid and TRGB measurements. Those are in gray, and then in red are the supernova hosts. So when I talk about the scatter increasing, like this is the figure in my head that I'm thinking about. But I have a little caveat in sort of handwriting font that this isn't, the gray points are just literature points. So they're not using the same method. They're not controlled for in the same way that like the set of red measurements are. So, it could be the luck of the draw at some level. So we do have to be a little bit careful with plots like this. But it does look like, and the high signal to noise, the high signal to noise regime, where we're only talking about a couple of orbits on HST, that we do come to conclusions. So on the anchor differences, at least with the CCHP measurement that we did last year by Insung Zhang, our calibration in 4258 and our calibration in the LMC agree extremely well. So maybe Dan could comment a little bit on this, but in Shoes, there are some differences between the calibrations with different anchors, but they're also different metallicity, different samples, so.
Yeah, right. Yeah, so yeah, our anchors, I think, disagree a little bit more, but I just say that I think they're supposed to disagree a little bit. Just it's 1.5, 2 sigma. This should just happen statistically. And this is, I also know this is kind of will get tightened up a bit, but yes, there is kind of some small disagreements with the anchors. I would say, I guess, just kind of for some more context, like what Suhail's asking is in the distance ladder, your first rung is measurements of the anchors. So like in this plot is the LMC. And then the next rung is kind of what we call the calibrators or supernova hosts or something. And I think the CCHP has really done a great job recently of just kind of building their anchor set. So it's not just LMC or NGC 4258. It's, they now have, and I think in Wendy's last review is 4 or up to 7 different anchors. And so kind of Shoes also has 5 or 7 anchors. So it seems to me like it's still, if you want to look at one place, you would look at the anchors, because it's just, if it's in the anchors, that first rung, it just propagates easiest through everything. And anytime anyone makes a kind of relative comparison, it seems just like an offset. You're not seeing any brightness or host galaxy dependent thing. So it feels to me, if there is a real problem, it's kind of some fundamental thing that's propagating into the anchors themselves. But right now, I don't think there's a great idea of what that is on any front.
All right, thank you. So actually, what Suhail asked, it kind of like leads me to the next follow-up question about this is, aside from the use of Cepheids and TRGB, what were the other differences between the two CCHB and SHU's analysis?
Rachael, do you want to take this?
Yeah, so I put in a slide 20. But yeah, so we use different methods. We have different pipelines, different people, obviously. But we also have different supernova samples. So CCHP uses the CSP sample. That's the Carnegie Supernova Project, which has been a long-range project at the Las Campanas observatories. And the SHU's et al. Use Dan's SuperCal sample. I think it's okay. Can I call it Dan's sample? The SuperCal sample, it's a big team. Yeah, it's a big team. The samples are fundamentally different. CSP is really going after, it's sort of the artisanal supernova sample is one way to think about it, whereas the SuperCal sample is really everything, trying to get everything as homogenized as possible. And it's just two different philosophical, I think, approaches that actually come up with just beautiful results. But in Friedman et al. 2019, we actually tried our calibration of the TRGB galaxies with both supernova samples. And so this plot is showing you on the top what the CSP using the Carnegie Supernova Project using our TRGB distances calibration. And the bottom plot is the SuperCal, but using the TRGB calibration. And those big thick arrows are showing you basically where the mean is. So you basically take these distributions and you get, the highest likelihood H naught from them. So the values that you actually get are reported in that paper. And they differ by about 1% just by switching these samples. There's objective and subjective reasons why either one of them might be the one you want to take. But I do think it's important to keep that in mind. I love how Dan's is this beautiful probability distribution. The other distribution's a little uglier, but this is kind of where I always try to say, this is Team Supernova's work, and I don't want to like impose, it's not what I do day to day. So
I don't think anyone's ever called my probability distribution beautiful, so thank you. Yeah, I mean, right, so these are kind of two different approaches. My one knock on kind of the Burns-Out thing is just that they're using CSP for the Hubble flow, and then a lot of the calibrators are not CSP, so you lose a little bit of that homogeneity. But overall, I mean, I am happy with a 0.6 difference in H naught for a very different approach. And like, I don't know, like, I feel like all of the kind of moves of kind of getting rid of the Hubble tension, it goes in waves of what's hot and what's not. And the supernova side was really getting picked on a lot like a couple years ago, and that seems to have settled down a bit. Now it feels like there's like a Cepheids versus TRGB wave that's going on. But the supernova side has been seeming pretty secure right now.
Okay, let me see if I understand. So these samples are all in the Hubble flow. This is not not in the anchor.
Right. So yeah, when Chris Burns did this, all of the Hubble flow supernovae were from this great CSP sample, but the calibrators, as Rachael said, were really volume limited. So you have to go back to like a long time, 30 years, 40 years. And then, CSP just didn't exist then. So if there's any differences between how CSP did it and some older survey, you're very sensitive to that. But like, I actually think the biggest difference between CSP and SuperCal is how you treat the host galaxy mass relation. which is getting a lot of focus. So it's not even, I think, the calibration. And that's just kind of getting better with more supernovae. So
yeah, that was my partial understanding of what happens sometimes with our with the actual MB values that we get, has a lot to do with the host mass.
Right, because yeah,
correction and how
right.
and how TRGB and Cepheid sample different parts of that relation, and then how you apply it. But since I have someone here who actually understands that in more nuance.
Yeah, right.
Yeah.
If you didn't do the mass correction, you'd get actually the CSP would get something higher than SuperCal. So it depends how you do that correction. And it's difficult.
So Behnam has a question, and then Suhail.
Yeah, it was partially answered by Dan. My question was, how different are the standardization of these two supernova samples, like the light curve and other parameters? You said that one of them.
Yeah, so there's a lot of differences that they went into these two numbers. So like for SuperCal, we use this fitter called SALT2. For CSP, they use Snoopy, and in the CSP sample, they do different ways of standardization. Actually, Suhail did this great analysis looking at near infrared supernovae, which CSP kind of also does. So CSP does near infrared and optical and some kind of mishmash. And Suhail was seeing also kind of, if you use Cepheids, a high value of the Hubble constant. So and even recently there's been like, don't use type 1a supernovae, use type 2 supernovae, which I think are pretty crappy standard candles. Sorry, and you get the same value of H0. So it is seeming like kind of different supernovae that you use. You kind of you go with the expectation of the what's calibrating you.
Okay, and Suhail?
So I heard 2 points. The first, which I think is very cool, which is what both of you touched upon, is that CSP is inherently a targeted follow-up program, and therefore like your mass distribution is probably by definition not going to follow the underlying host galaxy mass distribution, whereas SuperCal is all sorts of surveys like CFA, CSP, and like untargeted ones as well. And the TRGBs also like populate both old and young environments. So in this case, like, we can sort of see that the impact of environmental dependence of the Hubble residuals is probably not that high, or like it's nice to see that level of agreement when we're looking at something that's targeted versus something that's like a search and follow up on the same system or something. I guess maybe Dan can comment on that a bit more in terms of like looking at subsamples within SuperCal that are untargeted. Also, like type 2P is really cool, but not like from the expanding photosphere method. I think they would be like amazing independent angular diameter distance probes, and I'm really waiting for like that super cool spectral modeling stuff. Yeah, I'm not very familiar with the standard candle things, but I just thought if type 2Ps are mentioned, I think that's super cool. But yeah, I think like if with subsamples also we can see within SuperCal that untargeted surveys are giving us like the CFA is giving us a similar answer to the CSP. That's at least seeing that in the mass space, the host dependence is low.
Okay, anyone wants to reply to that or continue on that?
I was also going to say there is also a lot of bias even in our calibrator sample, which is the set of supernovae within this volume that we can measure distances. Like they're all within very narrow ranges of RA, which happen to be when different parts of the world have really good weather for sustained periods of time to collect the data. Things like that are also built into our calibrator sample, which then, I mean, the 1A part, the Hubble flow 1A part always feels like the part that's reached some level of statistics where you can subdivide the sample and run these tests at high confidence to understand what's going on.
Yeah, agreed.
Yeah. No, you
yeah,
go ahead.
As you say, one thing I keep hearing is like, and let's just wait for like LSST to come, and they're gonna have like have their own new calibrator sample. And the problem is it won't. You get one calibrator supernova per year that's kind of close enough to do these measurements. So It's just, we've done what we can, and you're kind of limited by the rate and our place in the universe. So you're stuck with what you got here.
Yeah, in my grant speak, if we want to increase the supernova 1A sample, calibrator sample, we have to increase our volume that we can measure distances. That's the pitch. But how practical that really is, that might be 5 or 10 years away until we have those kinds of facilities. Like with HST, we're pretty much at our limit, I think. I mean, the shoes, what Adam has done over the past decade with really using HST to its maximum potential, which I think is because he's at Space Telescope and knows all these, I don't want to call them secrets, but he knows these details, has been really incredible, but we're probably maxed out. JW is amazing. It's coming soon. The field of view is really tiny. And so it's going to have its own issues, and we have to start from scratch building our calibration samples if we want to do a 1 anchor system, and its lifetime is limited as well. Maybe, I mean, there should be a post coolant mission that I think is like at 98% confidence, that's 10 years. But I'm not sure it's going to be a 30-year facility like HST, which is what has let us get here, I think. So yeah.
Okay, thanks. So I'm gonna come back to the future prospects towards the end. So let's wrap up this part of the discussion. Just wanted to make sure that I understand. So the first plot that we were looking at was showing the differences in the supernova, in the distance modulus. So the one before this, I think. Yeah, this one. So you, is the conclusion that these differences can be exactly translated to the differences in the Hubble parameter, or is there more than that? So is this not enough to explain the difference in Hubble parameter?
I think this accounts for the bulk of it.
Okay.
There's a little bit from that supernova 1A, and then there's probably a little bit from the fact that until Wendy's most recent paper, which I honestly haven't been able to digest completely to the level of nuance that I'd like to have. There's maybe a little bit in the fact that we have different anchors and different combinations of anchors that might give you a tiny shift, but this rung is where most of the difference comes from.
Okay.
Which may be from our calibrations, but this is where, this is where it lives.
Okay, thank you very much. So let's wrap up this and move to the next topic. So let's talk about Behnam's reanalysis. So Behnam, if you could give like a few minutes summary of what you've done, and then we can open the panel to discussion.
Sure. Should I show some slides, or should I just explain without?
If you can explain without, that would be great. But if you want, we can also show a couple of slides. Yeah.
Sure. No, maybe just slide number 6, which is just a nice galaxy, and I can start up. So in our work, we wanted to basically, as independently as possible, reanalysis as many details, do the reanalysis of the data used by the SHOES project in as different way as we could. And
sorry, Behnam, you have some sort of noise. Maybe you're touching the microphone or something.
Okay, I try to hold it. So yeah, so this galaxy NGC 5584 is one of the 19 supernova host galaxies used by SHOES for calibrating type 1a supernovae luminosities. And this one has been, so the Cepheids in this one that you can see in this figure, the left and right are in two different bands. I can go to the details later, and you can see the Cepheids. The Cepheids in this galaxy have been used by SHOES to basically, it has been used in obtaining the periods and mean magnitudes in V and I bands of 9 other supernova host galaxies. So that was the reason we picked this galaxy. And then we performed, so we got the raw data from the archives to some, basically the first few steps of data calibration is standard. You should do the standard things that everybody else has to do with HST data. And we used the standard softwares, the result pack. But when we started basically the photometry, and then we tried to do it differently. So we use different tools. The principles are the same, like the principles of point spread function photometry of stars is the same, but we use different tools. And after having the fluxes at different epochs, then we used a completely different method for template light curve fittings to obtain the period and the mean magnitudes or mean luminosity. And then the rest is just comes out, right? So after that, it's then assuming or adopting a period luminosity calibration, and then you will have the distance. So in all those steps that I explained, we couldn't find any hint that we could say that, okay, in this step of the analysis, there might be a problem, or there's something that shoes might have done wrong, and using that, we might solve the Hubble constant issue. But we can discuss it later. I agree that it's just one galaxy, and I explained to you why we picked it. And a similar study should be done also for other galaxies. I think I can stop here, and then we can start the discussion.
Thank you. Dan has a question. Let's go with that.
No, I guess I especially want to say I think this is awesome work. Yeah. So one thing that I've seen about this kind of response to this work is, yeah, this thing that, well, this is just one galaxy, and there's just kind of this question of like kind of how much has shoes been reanalyzed. And so I just wanted to say two things that maybe Ben can talk about why this galaxy. And I think this galaxy is just a really good, normal, rich galaxy. So first, like a lot of the people, Wendy Berry, who kind of lead the CCHP team, they did the Cepheid key project beforehand. And that was a totally kind of independent measurement. And they got H naught of 74 plus or minus 2. So like, I don't want it to, this work to seem like it's the first time this has ever been done by anyone outside of shoes, because, Cepheid has this long history. And second, I think shoes has kind of gotten reanalyzed like crazy, once every couple of weeks. And I think what makes this paper different is it goes to raw pixels, but there's still 100 steps after kind of the photometry, and that's all getting reanalyzed. So I think what this paper is showing is, could the Hubble tension be explained away in the photometry stage, not kind of due to a new reanalysis? It gets reanalyzed a ton. So just want to kind of clarify kind of where this sits along the line of reanalyses.
Maybe just one point. I agree. Thanks for basically clarifying that further. Maybe the difference in this study was that, so out of these 19 galaxies, 9 of them has been observed by a new instrument, Wide-Field Camera 3, and the new band F350 LP, which you can see on the left of this left panel of this figure. So these data of shoes hasn't been, as far as I know, hasn't been analyzed to this level of pixels as Dan elaborated by any other team. So that was basically the difference. But I agree that, well, Cepheid and Cepheid analysis with HSTs has been done for decades, and the analysis that we did shows that, at least in the photometry part, although it's just one galaxy, but I mean, it's safe to assume that shoes have done the same method that they have done for this galaxy to the other galaxies as well. Therefore, it sort of lowers the chance that the problem can be, as Dan also said in the photometry part.
So do you expect it to be different? You get a different result if you analyze another galaxy like this? Or in other words, is this galaxy a typical one? Or is it a special one?
No, it's in fact, so its specialty is not lying on its nature. It's because it has been observed. Maybe maybe then this part you can go to slide 7, so I can elaborate more. So yeah, so these are the HST observations. This is a figure from Reese et al. 2016. These are the HST observations of all these 19 supernova host galaxies. And you can see a bulk of them, around 10, I think exactly 10, have been observed by older instruments. And then on the right side of this figure, so the x-axis is time, around half of these have been observed by the new instrument, sorry, the new camera, but not for all of them. So for these 9 galaxies, the time series data which you need for measuring the period has been obtained using F350 LP band. Let's just short call it LP band, and the purple one. And this band covers V and I, which are 555 and 814.
Sorry, let me just interrupt you for people who are not very familiar with these terms. Can you tell us, like, what's the significance of these bands? What do they mean? What's the differences between them?
So they cover different wavelengths. So 555 is equivalent to or very close to the V band, and 814 is equivalent to the I band, and this LP band covers the other 2.
So does that mean it's important because of dust extinction, or why is it important to measure in different bands?
So you would need the mean magnitudes in the optical or yes, in the optical bands, which are 555 and 814, because you would need the color of the Cepheids for some corrections. But the main magnitude comes from the red one, F160W. This is near infrared band. But the main measurement comes from this band, the red one, but you would need the color also in the other 2. But the resolution, so the near infrared band is in the IR channel of this camera in HST. The resolution is lower. It's harder to use only that to detect Cepheids and to measure their brightness in different time epochs. I mean, it's possible, but it's difficult. So usually you go to the optical ones for having the magnitudes in different epochs and having the period. So this LP band covers in the wavelength V and I bands. It makes it easier to detect more Cepheids and measure their the brightness in different epochs. That's why it has been used for observations of 9 of these supernova host galaxies. And then in V and I, these host galaxies have been observed. These 9 host galaxies have been observed only a few times. Therefore, it's not enough to have the period from those bands. The period, so the light curve and the period comes from the LP band, but we need V and I mean magnitudes. So Shoes has used a few observations in V and I, more observations in LP, then found a relation between, sorry, before that I should say, so for this galaxy NGC 5584, the light curves are relatively complete in all these bands, LP, V, and I. So then they have used these to drive a relation between amplitude ratios and period. And then they assumed, logically, that Cepheids in other galaxies also behave similarly. Therefore, yeah, maybe next slide would be good here, 8. And so the left panel shows a relation they found between amplitude ratios and the period. And then they assume that these relations hold for all the Cepheids in other galaxies, and then correct for the random phase observations of Cepheids in other galaxies in VNI band. So that's Charlotte, coming back to the question. This is the reason NGC 584 is special, not anything in nature, and it's one of the host galaxies that has the largest number of Cepheids. So it was good for basically checking and cross-checking of the results.
Okay, thank you. Dan has a comment or question.
Yeah, I just wanted to echo back a phrase Rachel used earlier of kind of that whatever the problem is nuanced. So like a different way of saying that is it embarrassing to the people who did the measurement, which I think for most of us observers is how we think about it. Like, did we do something that is just going to embarrass us? And I think with this analysis, like looking at photometry, that I put in the category of like, if you get it wrong, that's kind of embarrassed, like you'll be embarrassed. Like it's not interesting. Like just you did some weird PSF measurement. And what's kind of really nice about this is it's just kind of ruling out the things that could be kind of embarrassing, and whatever does resolve the Hubble tension, whether it's something local or new physics or whatever, it's interesting. And I think that's the point. I mean, that could be astrophysical, that could be cosmological, we don't know, but it's not, it's kind of not at this pixel level.
Good, thank you. So Rachel or Suhail, do you have anything that you want to add? Rachel?
I just want to say, whenever I say I think I might have used this phrase too, it was just one galaxy. It's a beautiful study. I'm not trying to say, oh, it's just one galaxy. I mean, it's a beautiful study, and I do feel better. But we're modeling a system, so I really hope this is step one of a bigger project. We'll see. This is exactly how I would do it too. So I mean, I don't mean it that way. I really don't mean it that way.
No worries. Thanks, and I agree that this should be like the start, and yeah, maybe this galaxy is just one of the well-behaved ones. We don't know. We should continue such studies.
Yeah, if you're sitting on panels, fund these kinds of studies. They're really good.
So I'm going to just ask the question I asked again, but just the part that, do you expect this to be different if you did the same thing for the other galaxies? Just very short answer, basically, yes or no, or maybe.
You're asking me, right?
Yes.
I'm not sure. I don't know, honestly. It may be, so it may not. I don't know. Okay, so it has to be done before. I think so. Yeah, it has to be done. Okay. All right, so let's wrap this topic up as well, and move to the next one, and that's the hot off the press Morzel papers. Suhail, could you give us a short introduction to what it is, and then we can open the panel for questions.
Sure, awesome. So just for context, I've been quite excited about Type 1e supernovae. Edward, Ariel, Joel, and I have been looking for lens supernovae, which we think are super cool as physical systems, as well as for measuring H0. We were also super excited about dust properties in Type 1e supernova hosts using the near-infrared Type 1e supernovae standard candles recently, and looking at what the origin of the host galaxy mass step is. And we just cumulatively looked at Dan and Dylan's paper, staring at it and went like, could we do this for Cepheids? And I think we said this repeatedly to each other enough on Slack that somebody wrote a piece of code, and then we just said we wanted to write that. So that was a roundabout sort of context for why we did it. But what is the reason for sort of getting into this? So we know that in order to use Cepheid distances, we need to correct their luminosity for the correlation with the period and the metallicity, but also for the color, which is what we know as the Wesenheit relation. And this Besonite coefficient, which multiplies the V minus I color that Behnam was talking about, is essentially correcting the H band apparent magnitude in order to give you corrected apparent magnitude with which we get a distance to that galaxy. Now, in order to, or rather in the fiducial analysis, the value of this Besonite relation has been fixed using a known galactic dust law with a particular total to selective absorption ratio. So this is what gives you the steepness of the dust law. It's just the total absorption divided by the color excess. And what we were sort of interested in was that the motivation there being, we know from both studies of our galaxy as well as studies of the local group, so like looking at the LMC, the SMC, as well as like type 1 supernova hosts in the nearby and distant universe, that this total to selective absorption ratio can have wildly different values that are differing from that canonical value of about 3.1. And of course, this impact that we're looking at, and this is typically done in the optical bands, but what we're looking for is in the near infrared. And what we wanted to see was, given this diversity, what is the impact of having these potentially different dust laws? Because we know that the motivation there is that they wouldn't be the same. What it actually comes out to be, that is what we wanted to fit from the data. So what we did was we just took the this FE data that was there in combination with updates to the LMC and Milky Way anchors, and we fitted a different coefficient of the Besonite relation for each galaxy. And what we find there is, like, because we're not like, we find there that like treating them as color excesses for each individual Cepheid, the case in which we have different values of this RH or RE parameter that we have, which is essentially like the Besonite relation for the color, but is sort of like the H band total to selective absorption ratio. So the reason I wanted to emphasize that is that this value in absolute terms is a lot smaller than what is there in the optical. That's why the Schu's team does this cool work in the infrared. And what we then find is that if we do account for these differences, we do see a significant decrease in the tension in the sense that like it's not negligible if we treat these color excesses. This comes to about 2.7 sigma with the central value slightly shifted lower and error bars slightly higher. Also, what Edbar did in follow-up papers, or in the follow-up paper, was to look at a different contribution of taking the uncertainty from the fact that we can't deconvolve the color excess, what of that is coming from dust and what's from the temperature, as well as like looking for uncertainties or like looking to account for uncertainties that are coming because of taking the oxygen abundances for the metallicity instead of the iron abundances, and looking at that difference and basically Monte Carloing what kind of error that we would get. And then that in the more updated paper, if we do take if we take the Gaia parallaxes for the companions instead of the Cepheids, we find a slightly lower H0 as well by about a delta H0 of 1. If we take the fiducial value with the uncertainty, that is with the parallaxes from the Cepheids themselves, the tension's at about a 2.3 sigma level. So I would say like the aim of this is to see where exactly like are we in terms of our systematic uncertainty budget, and how do we like then start to improve this? Because this is not like, we're not saying like here that this is going to like be a significant difference from the fiducial analysis. However, like these are systematics that we want to like start to overcome when we're thinking about a 1% level of the distance scale, and we think that's important. Yeah. So
thank you very much. Does anyone want to make a comment about this paper? You know that we had a lot of comments before.
I want to, but can we see some plots just so it's a little easier to kind of follow along? I think Suhail put some nice plots up.
put them, yeah.
Okay, yeah, this is a really good one. Yeah, this is a perfect one. Okay, so I guess I just want to say first, and Suhail and I work together, so I can rib him up just a little bit, is like the the first paper that came out was titled "Another One Bites the Dust," which I think I was seeing what now tells me that they just really like Queen or something. So, so it's that. But I think that was a quite sensationalist title, and I think to just say, hey, this whole H0 tension, it's just dust. Basically, I think even because Suhail's team would now say that way, you're just changing a lot of intrinsic stuff, and that's kind of hard to get away with. And if you just want to change the dust way, then it's kind of what Suhail was just saying. You could kind of lower the tension, still something above 70, but it gets lower. So yeah, I first just want to say something about that title. Okay, so about this plot, and I want to dig in on it because kind of one thing Suhail and I have talked about since is the idea of things seeming kind of like non-Copernican. But what I mean by that is it's like our place in the universe is special, or kind of the dust around us is special dust. And as Suhail said, kind of I've done a lot of work with Dylan Brout on kind of showing that maybe dust in our Milky Way isn't like dust around supernovae. So there's definitely kind of a lot of promise in this direction. And kind of what you could see in this figure 4 here is that the first 4 galaxies, those are kind of what we are calling the anchor galaxies, and then the all the other ones, those are the calibrator galaxies. And basically, kind of it looks, you can see by eye, like there's some drop in the orange points are around 0.4, and then everything after that is like less than 0.2, right? So that basically means like for some reason the galaxies closest to us have just very different dust. Then suddenly when you're 8 megaparsecs away, dust just changes. And so that's why I say kind of it seems non-Copernican, which is very weird. So I think Suhail tried to address this a little bit with this mu point, but you could see this just in figure 4. So what I think this is due to is if you just look at the uncertainties in figure 4, so the y-axis uncertainties, you can see that anything that's nearby, because we can kind of resolve these galaxies, we have kind of just more Cepheids, better information. The noise is much smaller. So just look at the size of the error bars for the anchor galaxies versus the calibrator galaxies. So it's very clear you get factors of 2 or 3 kind of in the mean size of the uncertainty. And this has kind of been a well-known problem in the supernova community, that whenever you're solving for kind of a dust law color luminosity relation, the noise basically has no relation with luminosity. So if you have color noise, its relation is 0. It should just pull your effective R sub W down because noise is just noise. So if you're looking at signal, what you do for the anchor galaxies, you're going to get this high R sub W. But as soon as your measurements start getting less resolved, less signal to noise, you're effectively going to get whatever kind of mean of your prior or anything. But that's a measurement problem, and the right thing to do is to kind of solve for underlying populations and put priors on. But so I am nervous about kind of saying, hey, there's just some non-Copernican difference, because you could see from this plot directly that there's very different noise properties, and these need to be taken account of.
Let me summarize what you said, and you can say if it's right. Are you saying that you think that they're fitting to the noise rather than to a signal?
I mean, you could see in all the calibrated galaxies. I mean, that's big scatter, big noise, and I mean it's touching 0. So I mean this is kind of much lower dust, weirder dust than even supernovae, which is supposed to have exploding and doing all sorts of weird things are. So yes, I think it's the noise that are kind of pulling these down. Now, what I really liked about Suhail's team's analysis is that I do think kind of what was in shoes was kind of simplistic, and I think this is really kind of focusing us on doing better. But I don't think the kind of change in H0 is as dramatic as this, which is getting pulled down by noise.
So, Hale, do you want to come back?
Sure. Yeah, I think so. So 2 things about that. Let's start with the noise part. I think the way in which it enters the fate is via this sigma dot that's in the sort of table 4 of the analysis, and you can see the plot on the right hand side. Like that's how correlated with distance. So you see the sigma dot median is more or less like flat for like the most close by anchor, which I think is 1365. I mean, apart from M101, of course, and the farthest out being 1309, like at almost redshift 0.007. So I think I'm not sure like whether we're more uncertain there. We might be like fitting fewer Cepheids, and that is like where the root n error is coming. And I'm sure like doing something where maybe we have independent dust estimates for these galaxies would be great. But I'm not sure
can you say what sigma total is? I don't remember. I don't know what the plot is.
Okay, sorry. So the right hand side is basically the measured distance from your 2016 paper, and sigma dot is the uncertainty on each individual Cepheid in that host, and this is just the median of that as a function of the distance. And we don't see that there's any.
Sure, but that's a different thing. So how the distance comes out, right? It depends. You're doing the measurement in the near infrareds, you're less sensitive. If you're measuring R sub W, you're sensitive to all the optical noise, right? So the whole thing with the shoes measurement is that you do things in the near infrared, so you don't have to care so much about the optical. You're just using the optical for discovery. If you're measuring anything that's to do with color, reddening, you need the optical to get the leverage. So you have different kinds of noise compared to what's in that right plot versus in the left plot. So I'm not sure. I think what you're showing from the right is right for the near infrared, but it's a different story. I mean, you could see it in your error bars in figure 4. Like there's a clear difference in the size of the error bars that has to come from somewhere.
Right, but like, so that could just be we have fewer Cepheids in those galaxies than the anchors, right? Like that's.
Yeah, I mean, we've looked since your paper. We looked, and there is much more noise just because you have crowding, more effects of crowding for things that are further away, blending, whatever you want to call it. So I mean this is a real thing. I mean, yes, you do have less Cepheids for some, but the impact of blending is worse for calibrators. So you're catching a real thing in this figure 4.
So the error budget that's given in the that's what I've plotted on the right hand side, and that's what I'm saying is not different for the different distances. So
right. That's a different kind of error budget.
Right, and that's what goes into the final linear model where you have your.
Okay, that's good. That's good to know. Okay, yeah. So I would not use that error because you're taking on all the optical effects too. And that's the whole thing with reddening is that you're sensitive to everything because you're trying to fit that slope, as you know.
All right, I thought there were like some error flows that were folded in there. Maybe that's something that we should then just discuss as to what should be the right way of doing that.
Yeah.
But so I don't think that. So we're not trying to say that there's something like systematically different. So like, could you go to the previous slide? I think that's the one, slide 29. Yes. So this is the case where we're taking R being like an RH, which is sort of like, it's multiplying the color excess, not the observed color. And here,
sorry, what's color excess again?
Right. So essentially, we're just deconvolving. So this is quite simple, and in that case, like what we do is we just separate the observed color into a mean color and an excess from that mean for each Cepheid. So that like we don't have a large sort of absolute value of the observed color, which would be typically 1 mag, and then we're multiplying that with a small difference. We might get large differences in eta. We're now just looking at an excess from a mean color for in the V minus I, and we're multiplying that with like so assuming like a color excess is twiddles like dust, we would then multiply that with these slopes of the color luminosity relation, and here you see. So I think that might be why it's confusing. Maybe I should have like pointed to this plot before. Here you can see that where we see that difference. Most of the host galaxies land in agreement, like within a sigma with the anchors. And we think that they're like that smaller difference, like the fact that the anchors on average are a bit higher RE, is within the statistical fluctuation. So that's why I'm not sure that like, so in that way, like we wouldn't infer something being non-Copernican because we don't think there's something at a particular distance. So that being the first point, but the second one also being that like we don't have like a clear distance separation, right? Like the mega maze is farther out than M101. So I'm not sure if it's like, it's just like, it could just be a statistical fluctuation where we have like 3 out of 22 points that are slightly higher than like the other 19. So that's sort of what I wanted to say to that point.
Sorry, Dan, let me just interrupt you, see if the other panelists want to chip in. Rachael or Behnam, do you want to say something about this or have questions for Suhail or comments?
Not me.
No, I mean, in TRGB land, we're getting away from the dust.
Lucky, huh?
That's the whole plan.
Okay, Dan, please continue.
Yeah. I mean, I think if you'd averaged your yellow points and average your green points, there's a systematic difference, but that's enough to cause H0 to move by 1.5 kilometers per second. And I think the interesting question is one kind of, why is that? And I'm saying it's more your noise properties, and then two, kind of what's the best way to do it. So like, I mean, so I would like with you to just kind of do the full kind of Bayesian prior, like, solve for all the different components and do this out. I'm trying to tell Adam we should do the same, and yeah.
I'm starting getting that set up. I'm getting really like excited about it. It also involves making a lot of plots in PGM, which have all these like flowcharts, which are really fun to make just by themselves. But yeah, making those like latent variable plots and actually the using that functionality is something that we want to do, where we start disentangling the noise, the intrinsic and the extrinsic component, and then we say this part's definitely not in like correlated with the luminosity, and then we have population level priors as well as parameter level priors. Absolutely, I think this was just to see like, does it move, how much does it move, and like what is the sensitivity, and that's what I'm saying. Like it is like, if you look at the left-hand side plot, the values that you say take for the RE medians, they're very like, they're seen in the, say, the Fitzpatrick 2019 galactic law. So like seeing an RE of 0.1 is not like unheard of, right? Or like seeing it of 0.2 with the new dust law and having low RV, it's entirely possible. It's just as I don't think we're claiming, like, we're definitely not claiming that there's something that's systematically happening at distance between the anchors and the host. But like a fluctuation would be something that's entirely possible, given the prior range has like a width of say 0.3. So if you just divide that with square root of 3, like getting a shift of 0.1 is like within like statistical fluctuations. So sure. What would be cool is to get like, of course, which is really difficult, but to have more anchors there and like just have more points or like a prior on the R from other sources, like I don't know, Balmer decrement or some other population of stars. That would be really cool. But,
all right, let's wrap up the subject. Thanks for discussing this new work, and it sounds like new ideas have come out of it as well. Okay, let's move to the next topic and go back to TRGB. So there's been some other analysis of TRGB. For example, the Anand et al. Was mentioned during the pre-discussion. So what's the consistency between these other analyses and the CCHB analysis, or do they move towards the shoes values? Rachael, do you want to start?
Yeah, so Deep Anand, so I'm going to call him by his first name. So Deep is part of Tully's group at the University of Hawaii, and his thesis was trying to see how wrong I was. And we're pretty clear on that. One of his mentors is Ben Shapi, and we're postdocs together, so it's a fun thing. I think overall, in what I've conversed with Deep one-on-one, we're really happy with how much we agree. He's using a completely different pipeline to do his photometry. He is using a completely different tip of the red giant branch detection method to get his tip measurements. And he's also using a completely independent calibration of the tip of the red giant branch. So all in all, he is completely, it's not completely orthogonal, but orthogonal to what we're doing. He's also going into the same images and using the same images, and in some cases using a broader set of images from the archive, which we've only done for a handful of galaxies. So on the whole, I'm encouraged in terms of, this is exactly going back to the discussion we just had about the Cepheid galaxy, knowing all the places that things could have been wrong. it feels really good to come in as close as we are. That said, I think his work actually does illustrate some of the things where we do get different results. I'm encouraged by the difference. I'm encouraged by what we can learn from those differences.
Can you summarize the differences very quickly, just for people who don't know?
Yeah, so I'm not sure what the net difference is, because the last time we talked, we were seeing pretty good agreement within a few hundredths of a magnitude on most galaxies, which I think is happy. I mean, I'm happy with that, knowing all these differences, because in our internal CCHP work, we run multiple pipelines, multiple ways of doing things, and we see those same kinds of stuff. And I was really happy for him to, we publish a lot of it in our appendices, but we don't publish all of it for every galaxy, because I think that's a lot for everyone to look at. But he does see some differences at the end of the day, and some of it does come from the calibration method that they're using, which is a perfectly valid way to do calibration. It's just not what we elected to do. I can talk about the pros and cons, yeah, I'm comfortable with what his analysis has showed so far. And the places where I think we maybe are getting the biggest disagreements are where the data are tough, and it really could be the data, not these other steps. So I don't know who added some of the slides, but if they
yeah, I added one like deep slide that he had shown at one of these recent things. So can we pull that up for a second? I have one question for Rachel that I have.
Yep. Awesome.
But maybe it's like at the end of the
27.
Yeah, so right, okay, so yeah, this is from deep. So this is, I don't know, I'm not a TRGB person, but so this is the normal TRGB plot of, you're looking for the tip, and it's like where the derivative shoots up. Did I say that right, Rachel?
Yeah.
Okay, so these are some of the I think the furthest out supernovae where they disagree, which I is fine as far as I could tell. So the offset, I think deep typically says, is like 0.03 meg, which in the direction of shoes, which you could say is there, isn't there, I don't know. But my question was a little different. So there's this really nice paper by Taylor Hoyt recently, and it was looking at the LMC, and I tried to read it, and it was talking about like these different ranks, like rank 1, rank 2, rank 3, rank 4, and depending on kind of where in the galaxy you're looking, it's like you could see this tip in some with these different metrics. Okay, so but then there's like these further out supernovae ones, and my question is like, can you do this kind of rank system for this? And like, then do you like, is it right to compare like rank 1 of something nearby to these far out ones? It's kind of the same thing we were just talking about with Suhail, of like, you're comparing things close out with really good measurements to things further away with not so good measurements. How are you not susceptible to systematics?
Okay, so yes, there are gradations of measuring a tip. I think Taylor's paper really goes into what you can do and how you can separate these levels in the Large Magellanic Cloud. It is a long paper. It is a beautiful paper. I encourage folks to read it if they have the time. And Taylor's here at the conference too, so you can ping him on Slack if you have more questions, or have a meeting or whatever. So the answer is when we get out to photometry that starts to look like this, So if you guys are looking at this, it probably, you're not seeing the RGB, are you? Like, remember Astronomy 101, those RGBs, you know, that's not what the edge cases look like. They're messy like this. And a bunch of these, like, I don't see the RGB. This is really tickling the bottom. So if, I know you can't see my cursor, but if you look in the big panel, which is NGC 1316, you see that diagonal line along the side. So that's completeness. So most of that is cutting out, like, that's not astrophysical, that's the data. So what we mean by completeness in resolved stellar population photometry is it has to do with when we can be sure that we would recover a measurement if it's there. And so that straight line there is being driven mostly by the F606 band, the V band, which is very shallow in our observations. The way to get, you know, we had to optimize for this F814. And so the fact that that line, you know, is getting really close in these other galaxies, if you look for that same diagonal, is really close to where those tip measurements are, means we're really tickling the bottom of what's possible with these observations. In 555, so, you know, these are redder stars. So 555 versus 606. 606 has higher throughput. 555 is a bluer filter, and the tip stars are not as bright in that filter. So that's why the sensitivity is going down. But these completeness diagrams, in 1316, this is the CCHP data. I'm getting into the weeds here, but I think it's important to understand. In the CCHP data, we design these observations about measuring the tip. We measure the tip in the I band, which is equivalent to F814. They're very close, within about 1/100th of a magnitude for red giant stars. So we put all of our eggs in F8114, so to speak. So we have our high signal to noise there, and we are only using our color. Our F606 is only used to say this is probably a galaxy or this isn't a real source. And so that's how we can kind of get away with the signal to noise that we have. In these other measurements, these are using the backgrounds of the Cepheid observations. So you can see the little inset in that panel. That inset is showing you the HST footprint, and there's a red circle. And so for tip measurements, we don't use anything inside of that red circle. That's where the stellar populations are too complicated for the assumptions that we need to make in our method to get to the precision that we want for cosmology. So exterior to that circle is what is being used to measure the tip of the red giant branch. Now, these observations are optimized differently. They are optimized to get equal, or more or less equal, signal to noise in both bands, more or less, because you need that for the Cepheid measurements. So actually, I think probably the F814 is what's driving the incompleteness here, rather than the V band equivalent. And so that's part of what we're seeing here. Redder stars not being detected as well. Now, we do a lot of tests on this kind of incompleteness results. And we do that with artificial stars. So that's where we drop in artificial stars into our frames and bring them out to figure out what our completeness is and how that's biasing our measurement. So far, we find, using different results, using different assumptions, we kind of come out within our uncertainties, but it's definitely something really nuanced that we have to do, and it's not perfect yet. I think we could make these simulations much more complicated and ask some more interesting questions. But yeah, these are tough measurements, and it doesn't surprise me that we disagree in these galaxies.
So Rachel,
yeah.
These galaxies, the 4 smaller panels, you said that you don't use any of the measurements in the red circles.
Yes.
So am I right to say that the reason you see the difference is because you're not looking at the same red giants, basically, for these galaxies?
No, I mean, I think we're looking at the same photometry. They use the analysis pipeline that they use, that Deep uses, does different criteria tests for what they consider a good source and not a good source. So there's a little bit of artisanal cleaning that I would do that's not done here. And again, this is not a criticism. This is just a statement of where different methods do different things. And so, you know, some of our CMDs look a little different. There's a beautiful analysis that Taylor Hoyt, who's here, has done looking at where we actually think it's safe to do our tip measurements. And it gets really hard in these face-on galaxies, because in our work, we look at the surface brightness profile of the galaxy, and when we wait for the surface brightness profile to drop off, so we're pretty sure we're out in the halo. We're not getting confused by the outer disk of galaxies. So the outer disk of spirals has young stars. You know, the outer disk of the Milky Way goes out to about 25-ish kiloparsecs. So we want to be outside of that range where we're actually looking at metal poor stars. So there's just differences here in what we're doing. And so, yeah, I'm trying to read what Taylor posted.
Behnam, you have a comment or question?
Yeah, I have a question, which is probably because I'm not familiar with the details of TRGB method. And the question is, are there different methods for measuring the tip? And if there are, how different is their outcome?
Yeah, so if we could go to slide 16. Okay, so this is incredibly low resolution because I just snapped it from a talk and I'm really sorry. So this is from a series of papers. So some of Insung's thesis, that's the Jang and Lee 2017, some from our analysis of NGC 1365, which is one of our more distant galaxies, and then an edge detection plot that I believe came from my review. So over on the far right side are different edge detection techniques. Okay, so in the tip of the red giant branch, we're making these CMDs. We're looking at the red giant branch, and then we're gonna marginalize over color, and we're gonna make what's called a luminosity function, which is literally the number of stars per magnitude bin. And how you do that marginalization is something that different teams do different things. We have chosen to bin at the precision of our photometry, which is about 100th of a magnitude in most cases. I don't believe the numbers after 100th of a magnitude when they spit out of my pipeline. That's the noise. Different teams do slightly different things. And in this plot, we're doing different ways of measuring that edge. So a way that we commonly measure edges is to take the first derivative of a function and look for edges. And so this plot is giving 1, 2, 3, 4, 5, 6, 7, 8 different ways of measuring the edge. And that red point is a response function. That's just the first derivative function. And in several of our examples, we tried to make sure that our results were somewhat independent of what we chose. And we chose the one where we felt like we could the methodology that we've chosen is one where we believe we can derive the uncertainties, and they're very meaningful. Some of these edge detectors are doing so many things that it's very hard to track how the uncertainties are influencing things. And sometimes they're completely within that red peak that we're measuring, which is good and bad at the same time. But generally, these different edge detection techniques on a data set that, where you're definitely looking at red giant branch stars, even down to, the more challenging galaxies, give us similar results within the uncertainties that we quote. What DEEP does is a slightly different type of analysis. They're using a maximum likelihood analysis that is looking at that luminosity function, and it's actually fitting different relations for different parts of that diagram. There's an expected luminosity function coming from the asymptotic giant branch stars, and then there's a luminosity function that we expect from the red giant stars, and then there's a jump in the middle. And so their maximum likelihood analysis is fitting that relationship to the observed luminosity function and looking for that jump. It's a different, it's a great technique.
Sorry, Rachel, to interrupt you.
I was gonna say that would be D in this panel.
All right. Okay. So we need to wrap up and then start the. We don't have time, right? Yeah. So we've gone over time actually. So I'm gonna give you one last question, and hope that you all have some answer for it. So have any of your prior beliefs been impacted in any way, even small way, as a result of this discussion? Who wants to go first?
Yeah, I could start. Yeah, first, I really like talking about this. I feel like I learn a lot every time these kinds of things happen, and I know like our field can get pretty contentious, so I think it's just really good every time people talk and it's not that contentious. So I think Suhail and I have a plan of what to work on. I really like hearing Rachael explain kind of what's going on TRGB, because I'm still just learning about it. I think with just one general thing I want to say that I feel kind of listening to this is just that I really think the science is getting better, kind of on all fronts. Like, yeah, there's a lot of criticism being thrown every which way, and I think this topic is really important, and I think the criticism can be rough sometimes, but the science is definitely getting better. Like I look at these recent papers, and it's just like I don't know, there's just the level of complexity and the robustness of the results is just really improving. Kind of hearing people talk about it just makes me think more so.
Okay, thank you. Anyone else who wants to go next? Behnam, you want to go next?
Well, I really don't like using the word belief, but I learned a lot. One thing that was more or less clear and got clearer is that there are lots of complexities and there are lots of room to work on. One thing that I would like to highlight is that, yes, the focus of this panel discussion was and is on the difference between TRGB method and the Cepheid method. But if the result from CMB, which we don't want to discuss, was in the middle of the two, we wouldn't have a Hubble constant problem, right? This is something we wouldn't have this discussion. We shouldn't forget this. Almost all the direct methods are giving a Hubble constant larger than that of CMB. And both TRGB method and Cepheid method have been more or less consistent in time, and just the uncertainty was reducing, decreasing. And it was the CMB that, after the nice and precise measurements of Planck, has drifted away. So just wanted to highlight that. And I think one way to move forward would be to really pick those galaxies that TRGB and Cepheid method are giving too large differences, and then dig into them and see if we find something.
All right, thank you. Suhail?
Yeah, I think one thing I learned was that we're all very excited, and that's all that's really there. But like quoting from Wendy's recent paper, like I think it's interesting no matter what the number is, like even if it does agree with the standard model, I think that would be like such a phenomenal test because of the level at which like we're measuring distances. So I think it's just like we're all sort of kind of very excited to improve these uncertainties, get into like small details and like try and cross-check that instead of the way in which debates were historically posed as being like some sort of dichotomies. And I think that's something that's really cool. And like I've learned a lot about those details, at least by reading papers by the CCHP and Shu's teams, as well as the discussions right now. And it's really amazing. Like when I read something like the SMC has a detached eclipsing binary distance to 2%, I find that's amazing, given like in context of even day-to-day distances not being measured to that level of precision. So I find that's quite amazing when someone says that whatever in the nearby universe, but still we can measure it that well, and this is the level at which we're seeing disagreements. I think that's pretty amazing.
Thank you for the positive view. And finally, Rachael, any last comments?
Yeah, I really enjoy panels like this where we really talk about our measurements in depth and try to make sure everyone understands some of the details. And it feels like we talk more about our commonalities than we do about our differences. And when you're in this subfield where papers come out once a week that are kind of questioning your whole research focus. It's really great to have the opportunity to talk in this kind of forum and with this level of congeniality and like, let's sit down and solve this problem, because that's my focus. And I feel like I often get dragged into things where it's like, oh, attack shoes. I'm like, no, I'm not attacking shoes. That is hard work that we shouldn't attack each other. And I feel really hopeful. I feel really hopeful seeing people now publishing counterpoints, and I think that's good. I think that's healthy. I think if we weren't having counterpoints getting to the point of being published, we'd be in trouble. And so seeing more of that come up is a positive thing, and it should be good for our field to have counterpoints and to have discussions like this where we try to understand what we're saying and what we're doing, because there's a lot of nuance in our measurements, a lot of details, and this is where we iron them out.
All right, thanks a lot. Thanks everyone for joining, and also very special thanks to our panelists. So this is the end of the panel discussion, but we can go back to Sokoko and have continue some of these discussions.